Good afternoon. Hello, everybody. I'm Mark Asta, the Interim Dean of the College of Engineering. It's a true pleasure to welcome our Dean Society members, faculty, staff, students, and guests to this special evening. This is the celebration of our first semester in the Grimes Engineering Center, and And tonight will be the illumination of our new art light installation, the Strauch Hypercube. I have to say the building and the art piece are a true testament to the creativity, collaboration, and innovation that define our community. As we light this work later this evening, we celebrate not only the beauty of the art itself, but also the shared vision that brought this building into being. You will hear more about that vision a little later in this program. I want to extend our deepest gratitude to the generous donors whose vision and commitment have made this new center possible. Your contributions have not only brought the building itself to life, but also laid the foundation for vibrant student-facing programs, services, and opportunities that take place within its walls. And if you're fortunate enough to be on campus during the weekday and come in this building, it is just a beehive of activity. Every seat is taken, and it's really exceeding all of the faculty's expectations for what it was delivering to our students. Because of your support, this center serves as a welcoming and inspiring space where students learn, collaborate, and grow. It provides essential academic resources, mentorship programs, wellness initiatives, and community building activities that nurture both personal and professional development. Every student who walks through the doors of this building will benefit from the generosity and foresight of those who invested in their future. And so thank you to you all. Your philanthropy has created far more than a physical structure, even though the physical structure is pretty cool, as you're going to hear. It's built a lasting legacy of support and possibility. You've empowered generations of students to thrive and succeed, and for that, we really offer our heartfelt thanks. And so I'd like to lead some applause to all of you who contributed. As I said, this is really something that has captured the imagination of all of us in the college, and I think as a testament to that, we have many of our faculty colleagues who've also joined us tonight, and too many for me to actually introduce. So rather than introducing them, I would ask them to stand, and we can all appreciate them as well. Faculty. Yeah, look for their faces and try to find them and talk to them later in the event. So having so many join us on a Saturday afternoon speaks to the excitement and commitment our community has for the building and this occasion. So we know there are many challenges currently in higher education. I'm sure you all read the news. But amidst them, Berkeley continues to make incredible progress, thanks to the loyal support and generosity of the Dean Society members. Your contributions have been instrumental in our journey, and we are deeply grateful for your continued support. You're not just donors, but integral members of our community, and your role in our success cannot be overstated. Okay, so before getting into the program, just a couple of quick highlights of some things going on since the last time we met. So as of this afternoon, I've been watching the news carefully, and apparently we did not get a Nobel Prize today, I'm sad to say. But we did pretty well just very recently. As you may have heard, the UC system earned 5 Nobel Prizes, the most, yeah. That's the most ever awarded to a single institution in a single year. And of these 5, UC-affiliated faculty members, Berkeley's own Professor John Clark and Professor Omar Yaghi, shared Nobel Prizes in physics and chemistry, respectively, and Professor Yaghi is a member of the College of Engineering in the Material Science and Engineering Department. So those of you who've watched Berkeley football will notice a new addition to the helmets, the number 63. And if you're wondering what that is the total number of Nobel Prizes that we have earned at UC Berkeley. How about that? Yeah, that's right. So one of the downsides of that is parking is getting even rougher on campus now because they get the free parking place. Okay, so rankings, we continue to do well. We're once again ranked as the best public university in the country, and the College of Engineering is also top ranked alongside MIT and Stanford. The incredible achievements of our alums are a key factor in this success. One of the things this year that we're celebrating is aerospace engineering. This spring, our first class of aerospace engineering students will graduate. Believe it or not, this is the first new major that we had offered in the college in more than 25 years when we started bioengineering. So it's become really a remarkable programs, and the students have charted a new course in the college's history. They're doing internships with NASA. We have a new capstone course launching this fall that will see them flying their own designed drones out at Richmond Field Station. And the program has quickly become one of the most popular majors on campus. In fact, we've added a minor in aerospace engineering for students in other disciplines, and Professor Papadopoulos, who's here, the faculty director of aerospace engineering, would be happy to answer any questions you may have. Panos, you can raise your hand so people can find you later. So that experience may have catalyzed a little bit more ambition. We have 2 new majors. So remember, we hadn't done any in 25 years, and now we're adding 2 more. So next year will be the first year that we welcome students into our new electrical and computer engineering degree and into our environmental engineering degree. Demand for engineering degrees has never been higher, and we're feeling that here at Berkeley. This fall, Berkeley Engineering welcomed over 1,200 students, including our largest ever incoming class of transfer students with over 300. Yeah. It's kind of interesting to look at where we are now just compared to a few years ago. So we have 41% more students in the College of Engineering now than we did just a decade ago. So and yet our acceptance rates still stay in the single digits, which tells you about the demand for a Berkeley experience. We really have some of the brightest students from diverse geographies and backgrounds across the world. The growth of our student count and diversity are a testament to our commitment to providing a world-class education to all who seek it, along with the services and programs that support their success. You've hopefully learned a little bit about some of the programs that we are committed to helping support student success, and in fact, those are located right here on the first floor, this floor of the Grimes Engineering Center, and along the tour, you'll be able to see some of the spaces used for those programs. To meet the growing demand of students, the college is working in strong partnership with the campus to recruit top new faculty. So even with the budget challenges, the campus is not backing off their commitment to hiring new faculty, and we have a large number of faculty recruitments this year across all engineering disciplines. We are also innovating in our educational approaches to meet the demand. For example, we have stood up a new initiative that we're calling Engineering Plus AI, and as part of that, we're seeding new innovations to harness AI as a tool to enhance learning objectives and delivery of our education at scale. We're also investing in resources to enable increased access to co-curricular experiences for students. You saw some of the student teams out here in clubs. It's amazing how impactful those experiences are for advancing critical thinking, problem solving, hands-on experience, innovation, all of these things. As part of that, we've made a major investment out at Richmond Field Station for fabrication facilities to enable them to build their rockets and their cars and all the cool stuff that they're doing out there. So some of the teams using that facility are presenting here today. Okay, so that ends the highlights. There's much more to say, but I want to move into the program now and talk a little bit about the building that we're all in. Okay, so designed to inspire. What I want to do in this slide is really focus on what's at the bottom, even though the beauty of the building itself is quite inspiring, particularly the way that it's so transparent from the outside. You can see everything that's going on inside. Thanks to our generous partners, the Grimes Engineering Center was 100% philanthropically funded. Okay, so we knew that the Grimes Engineering Center would be a large and dynamic facility that would house a diverse range of programs, activities, and collaborations. So it was very important when we started planning how the building would be managed and what policies we'd put in place. We had to start by developing guiding principles that you see here. These principles embody our community values, values that inform our decisions, shape our policies, and define the standards to which we hold ourselves accountable. And I can't tell you the number of small tweaks we've had to make already in just a few months, and how much access any student group can get to this room or that room, and so forth. And so it's really been important to have these governing principles which have guided our decisions and really try to maximize the equitable use of the building across all of the people that use it. Okay, so the building has risen to 3 floors, and you'll hear how that was done from the next talk. It has over 83,000 gross square feet and was built on an existing foundation of the Bechtel Engineering Center, which was much, much smaller. So that was a challenge for structural engineering. And here's an overview of how centers' spaces are broadly organized. And so in the next talk by Professor Mosalam, you'll hear more about the building process that enabled us to do all this. And you can kind of see the cables out there for seismic fitting. So that's a little bit of a preview of what you'll hear about. Okay. All right, so let's go through the different levels. So on the floor below us, we call it the library level, we not only have the Kresge Engineering Library, which, let's see, okay, entrance to Kresge. Okay, so that's on the next slide, I see. All right. So in addition to that, we were able to expand the space out so that we can meet more demand from our student organizations. So we're hosting space that serves 40 student organizations. And in addition to that space, they're using reservable space in the building in large numbers. They're in fact the power users of the reservable rooms in the building. So let's see if the Kresge Library is next door. Nope. Okay, so let me go back. I always have to mention the Kresge Library because I spent so much time there when I was an undergraduate student myself that if I just walk in that building now, something about the smell of it activates in me a panic that I have a midterm the next day. And so if you spent any time there, you'll be reassured when you go down there that the smell has not changed. Okay. All right, so the first floor. This serves as the heart of the college's undergraduate community, home to academic support, mentoring, wellness programs, advising, professional development, and countless other initiatives that helps students thrive. Okay, floor 1 west, that's where we're sitting right now. Many of you will recognize this as the space we're currently sitting in, the Jarvis Auditorium. Right outside is the Raw Thrills Lounge and the Giancarlo Gallery. These 3 spaces make up the Jarvis Event Pavilion, and it is in constant use with events happening almost every day. It really has become like an event venue here. This semester alone, the building is hosting over 300 events. Yeah, that semester, 3 months, right? So, and many of them are being held in these spaces. Okay, second floor. You'll notice that this floor is full of flexible collaboration spaces, and they're always busy. In fact, the students will come in the morning and stake out their little area, and then one of the students from that group will go to class, and they'll hold the seat for them so that when they come back. So I don't know, that's not in our policies, but I've noticed it happening. The same people you'll see there in the morning and then in the afternoon. So this floor is also where our inclusive excellence and K-12 outreach programs are based. And the terraces around the building are especially popular. If you haven't already, take a moment to step outside, and you'll see just an incredible view. We think it's amongst the best in campus, and when Evans Hall goes down, it'll be even better. Okay, third floor. The floor is home to 3 marquee programs that we run in the college to support our undergraduate students. They really provide unparalleled opportunities for our students. The first is the Sutarja Center for Entrepreneurship and Technology, which equips students, professionals, and global partners with skills and entrepreneurial mindset needed to innovate, commercialize technology, and lead in the global economy. We have the Banatao Globe Center, which builds global connections by partnering with universities around the world to host visiting scholars and undergraduate students, fostering, very importantly, cross-cultural collaboration and academic exchange. And the Management, Entrepreneurship, and Technology program. This is a very successful program that challenges students to go beyond traditional academics by integrating business and engineering. It's a rigorous and highly selective program that allows students to earn degrees in both business and engineering simultaneously. And tonight, we'll celebrate the newest addition to the building, the Strauch Hypercube, suspended above the atrium from the roof. Okay, so that ends the first part of the program, and now it's my pleasure to be able to introduce the next speaker. This is Professor Khalid. You've learned from this short presentation what's going on inside the building, and what you're going to hear about next is the innovation, true innovation, that was behind building the structure itself. Berkeley, we innovate on so many scales, from microelectronics all the way up to building size like this. And so you're going to hear the story about the innovation that's gone into the structural engineering here. Professor Mosalam is a Psi Professor of Civil Engineering and the Director of the Pacific Earthquake Engineering Research Center, or PEER, we call it. And so with that, let me invite Professor Mosalam to the stage, and let's give him a welcome.
No, I would use. Thank you, Dean Asta, for the introduction, and thank you for having me. It's always a pleasure to speak about a real project which is started as a research project. We rarely see our research coming to an actual action, so it's really humbling to see that some research can see the daylight, and we're going to talk about the Illumination cube later. So. Well, good afternoon. I'm Khalid Mosalam. As the Dean said, I am a Professor of Structural Engineering. I'm also the Director of the Pacific Earthquake Engineering Research Center. And today, I will share how smart materials and smart testing are shaping resilience in Berkeley Grimes Engineering Center. And hopefully, this will be an example for many other buildings to follow. But before I start, I want to thank Rupa Garai. She is a principal in SOM who designed and executed the building. She shared her knowledge and some of her slides with me, which I'll share with you. I also would like to thank the staff of the Pacific Earthquake Engineering Research Center. Amarnas is here. And also the staff of the Civil and Environmental Engineering, the Structure Lab. They have done the tests I will share with you. But before I start, I am the PEER director. I have to tell you something about PEER. So PEER is an alliance of university, government, and industry. We focus on so-called performance-based engineering, such that buildings like this one protect life rather than destroy life, because we see what happened after earthquakes, and buildings can kill people. So we want buildings not to kill people, to protect life. But also we want them to recover fast. We are very much interested in so-called functional recovery. When an earthquake happens, which will happen, we would like operation to go back, especially for such an important campus like ours. We don't want any downtime. We don't want students going home. We want them to continue learning and the campus remain functioning. So our collaboration with our industry partner, SOM here, is actually the focus of this short presentation. But the work on earthquake resistant goes way back, even before I was born, meaning 30 years ago. So, no, a lot more. So I'll just show two examples that manifest the excellence in earthquake engineering. One of them that all of you know, and it was mentioned about the game, is the California Memorial Stadium. This is sitting right on Hayward Fault. You can't find that anywhere in the world. We are the only one who built right on top of the fault. Because we know how to solve the problem. This structure that straddles Hayward Fault, one of the most active faults, it was retrofitted using blocks. And the whole idea, and that's Earthquake 101, the whole idea of earthquake resistance, never fight nature. Don't fight the earthquake. Go with the ride. So that's exactly the idea, is the building is made of blocks that can accommodate the movement since the fault is going to move, so they have to move with it. Another phenomenal thing in this facility, and I have to disagree with my dean, really the best view you get it from the press box. And if you haven't done that, you should do it. This press box is another innovation in earthquake engineering. It's sitting on 16 pins, 16 dampers that allow it again to move and go with the ride if an earthquake happens, and it will happen, I repeat that. Another marvel is right from here, across from the Grimes Center, is the Hearst Memorial Mining. And this is registered in the National Register of Historic Places. It was retrofitted, again using a technology that was developed here, which is base isolation and energy dissipation. So it is sitting on 100 plus or 198 high damping rubber bearings and 24 viscous dampers, so it can dissipate that excessive energy that is feeding into the building when an earthquake happens. So the example of the Hearst mining is we are not only preserving history, we are preserving it by engineering the unknown future performance. And that's the biggest challenge. We don't know when an earthquake happens, how big it is. We have to anticipate what it is. We have to make sure that that performance is going to preserve this history. And that's a huge challenge that we take upon ourselves. So these projects, these two projects I just mentioned, there are many more, remind us that Berkeley not only preserves the past, but also redefines the future of seismic safety. Turning into the start of this innovation of the Grimes Center, earthquake solution, or most of the solution are one-time solution. And here is an example of a steel frame that has these steel braces that definitely preserve the integrity of the structure by deforming, by fracturing, and dissipating the energy. But then that's it. It's one-time solution. Then you have to go replace all these. Takes a lot of downtime. You have to find the right pieces. You have to find the right workers to do that. And there is going to be monetary losses, losses of function. But smart material can actually do better because they can give a recurring solution. And here is an example of two little wires. One is steel, one is a shape memory alloy. And you bend them, the steel stays deformed, and then the shape memory alloy goes back to the way it was. And that's the whole idea. And this is shape memory alloy 101 that I'm sure Mark Asta showed in his class, one way or the other, where a combination of temperature and the stress can lead to this so-called super elasticity behavior, or sometimes called pseudo elasticity, where you don't have permanent strain as the picture in the back. Instead, it self-center itself. And we still want the energy dissipation that's in this area, because that's important, but we want it to go back to the way it was, and that's the whole idea. So at normal room temperature, that is the material behavior we like to introduce into our buildings. And that's not new, really, because there is a daily use of this innovation. NASA use it in their airless tires, such that when they send a rover to the Mars, they don't put air in their tire, but the tire is going to deform. Then it needs to go back to its shape. Also, in the arterial applications, if one needs a stent, it's going to deform with the flow of the blood, and it needs to go back to its original shape. So what did we do? We took this idea, we put it in a tension rod. We have our 50 plus, exactly 53-year-old shaking table that's still going. Lots of innovation happen on this table. We still use it until today. And we came up with this type of steel structure that we can put these tension rods that you see them when you walk around the Grimes Center. You see them in a larger scale as a way of a proof of concept. Can we actually have a tension rod with that shape memory alloy at one end of it? What would it do if we give it a realistic ground motion through this shaking table? Is it really going to self-center? So that was a proof of concept, which indeed was proven, but that's not enough to do a design for such a landmark in the most important campus in the world. It needs a lot more of parameters so we can inform the designer what to do with this innovation. So this is the kind of tests we did not too far from here in the structure lab in Davis Hall, where we did 3 types of testing. When you design something like this, you want to make sure the weakest link is known. And the weakest link will be in how this shape memory alloy wire will be connected to the structure. And for that, we use this swag connection. And we want to make sure it's not going to fail. So there has to be some testing related to that. And then you test the device itself, but you test it in a full scale. And the shaken table was a smaller scale. Not only that, you have to test several of those to make sure quality assurance is guaranteed. And you test it to failure to see how far you can go with this thing. And then you put it in a system that you see this silver frame. The orange frame is not what we are testing. That's actually the reaction frame. But the silver frame is what we are testing. And if you look carefully, you see a diagonal with that shape memory alloy at the end of it. So you want to test it in a system. Then you inform the designer of the finding, and then they do their design, and they build it, and here we are enjoying their design. So here are 3 clips. The first clip is for this sway connection test. And you see it ruptures, and then we know what force would it take for that. And then you see one of these devices are tested in the middle, where these things work in tension, but they go slack in compression, which is intended. And you repeat that many, many cycles. You test several of these devices, and at the end, you pull on it until it fails. Then we know what is the failure load. And then you put it in that system that you see here, and we subject it to back and forth loading. And then if you look at these plots up here, you see actually that pseudo-elastic or super-elastic property, and the self-centering is actually happening. And that's another confirmation that this innovation is not just a far-out idea. So the key outcome of these tests are summarized here, where compared to conventional rods, tension rods, the shape memory alloy achieved roughly 20% lower peak drift. By peak drift, we mean when the structure moves sideways, how far that movement is. So that was reduced by 20%. That's not great, but what's really great is 60% reduction of the residual drift. When you go back, right, how much of this residual drift is, and it was 60%. And even more important than this, damage, when it happens in a structure, it's local damage that can lead to global collapse. And local damage always happen at some point that we call a plastic hinging, that lead to plastic rotation. Plastic means it doesn't recover, stay, and then you have to replace the member. So 90% of the plastic hinging in column was reduced. That's enormous. Another thing is 20% to lower demand on other members. It's not only the tension rod with shape memory alloy is the only member in the structure. There are other members. Actually, there is another innovation. You see it in the upper story called the BRB, which is also developed here in Berkeley. It's buckling restrained brace. And there is a force demand on this member that with the use of the shape memory alloy, it was reduced. That lead to a more sizable member and better architecture, no obstruction of the hypercube, and also it reduces cost. So that was another benefit. Another thing that's very important related to the functional recovery I mentioned, which is protection of the users of the building, which are the students, our most important asset on this campus, and also the content of the building. So the hypercube is an important piece of art that we don't want the floor movement to lead to its damage. The damage happens from the floor acceleration. When the floor accelerates, it leads to forces going to what's on top of this floor and lead to toppling of something or breaking of it. So there was a reduction of the floor acceleration as well with the use of this innovation. The location and existing old Bechtel Center were very important aspects in the design. This location for the, and this is not a bad word, for the brutalist architecture of the Bechtel building was actually hidden by Evans Hall. It was very hard to see it. Which is good, probably. And the whole idea of the Grimes Pavilion is to have that beauty that, and the inspiration that the dean talked about, that can balance the old and the new. And this is very important concept for architects. So that's what Grimes Center achieved. But there is one thing that we should know. We are 215 meters away from Hayward Fault. This time we are not on top of it. And that's not very long distance for seismic hazard. So we had to make sure that the designers are using the code specifications that are not lower than the expected seismic hazard in this site. And in Berkeley, in the Pierce Center, we work with Lawrence Berkeley National Lab. We have a project with them called SGMD. It's the Simulated Ground Motion Database. It's the largest database in the world. It's almost several billion grid points only in the Bay Area. The intention of this is to conduct a simulation on the supercomputer for envision different scenario of the movement of Hayward Fault. So when the Hayward Fault move, waves propagate, they solve the wave propagation problem considering the entire geology of the Bay Area. And they give you ground motion, XYZ, at every grid point of these several billion grid points. And we are the keeper of this data. So for different scenarios along the Hayward Fault, characterized by these stars, these are different in vision hypocenter where a fault may happen. And we have these billion time series. We can plot mean plus and minus standard deviation, and then we compare with the code spectra that is shown here in red. Grimes center sits in this band in terms of the expected mode of vibration of this center. And we are pretty good if we rely on the spectra that is defined by the code. So that was important, a check of reality. So we gave all this information to the designers, and according to SOM engineers, this is now their work, is the Grimes Center structure system followed these 6 steps. The first is, and these are typical steps of structure engineering working with the architects, is you have to assess the existing condition. And in this case, it was very unique because the existing condition is not just a site and soil type and whatnot. It's an actual building that you build on top of it. And then you fill out level 2 that you see here with that orange frames, and then these BRB that I mentioned of the interior frame that are shown in red. And then you add level 3, and then you put the SMA perimeter frame that's shown in blue, and finally you add the roof. So that's the whole design done in 1 minute. Huh? It's no big deal. But then it takes a lot of effort to put all these pieces together, a lot of hard work, and here I am showing the photo that shows this tension rod with the SMA where the crane ends up there. It had to be, by the way, pre-stressed to a specific value that was decided on by the testing that was done, such that it doesn't go slack. So there is quite a bit of a process that was included there. So we went from this brutalist architecture, analogous to our Worcester Hall, and we went to this beautiful pavilion here. We're very proud to say that Berkeley's culture of experimentation using our labs, generating valuable data, and exploring innovative smart material were effectively exercised to protect people, preserve assets, and shorten recovery time in the face of extreme events. So in closing, and circling back to Dean Asta's presentation, Grimes Center, designed to inspire, was possible thanks to the contributions. This accelerates journey from discovery to deployment, enabling rigorous research and testing that yield devices and actionable guidance to strengthen Berkeley's campus and the community as a whole, and more Nobel Prize laureates. With that, I stop. Thank you very much.
So I want to thank Khalid very much for the fantastic presentation. I think we need to take a moment to express that appreciation because he changed his travel plans to be with us tonight. He'll be taking a red-eye flight this evening to present at a conference on the East Coast tomorrow morning at 9 a.m. Yeah, and you might need that on your flight, yeah. Hopefully your presentation's already done for tomorrow morning, okay. Okay, so now just a few more words. Tonight's event would not be happening without the vision and inspiration of 2 individuals, the brothers Roger and Hans Strauch. They're trustees of the Moss Foundation. Roger has been a member of the college's engineering advisory board for many years and is a tremendous advocate and partner for the college and our students. As chairman of the Roda Group, an early-stage venture capital firm, Roger and his team invest in people, technologies, and companies addressing the consequences of climate change, natural resource contamination and scarcity, and the transition to a low low-carbon energy future. In addition to his business accomplishments, Roger is deeply involved in supporting a wide range of academic, artistic, and philanthropic initiatives. He leads the Moss Art Restitution Project. It's a global effort to recover Nazi-looted artifacts from his father's stepfamily, which has become the largest and most successful project of its kind in history. Hans Strauch is the founder, principal, and creative director of HDS Architecture. Over the course of his career, Hans has collaborated with leading real estate developers, property owners, and private institutions, both nationally and internationally. Together, Roger and Hans are trustees of the Moss Foundation, which provides support for humanitarian, educational, and cultural initiatives in the US, Europe, and Armenia. So we're going to welcome both Roger and Hans up in a minute. I also want to make one more introduction, and they will have the last word. We'll hear from the artist who brought that vision to life, Susan Narduli, principal and creative director of Narduli Studio. So with that, please join me in welcoming Roger to the stage, followed by the next two.
Good evening. Thanks so much, Dean Asta. Well, it's an exciting moment, and we're all going to be welcoming in a little bit more light tonight. And I'll have to be frank with you that it only occurred to us today that our project is somewhat related to the motto of Cal, Fiat Lux. My brother Hans and I are honored to dedicate Susan Narduli's marvelous, dynamic, impactful work of art in memory of our father, Karl Strauch. And we thought we'd tell you a little bit about him. Our father was born 103 years ago this month. He was a German refugee who graduated high school in Paris a few months before Hitler invaded France. He escaped arrest by the French for being German and the Germans for being a traitor, with the help of a customs officer in Portugal who looked the other way when Dad boarded a merchant marine vessel to the United States without the proper documentation to enter the country. A relative at Caltech, Pete Panofsky, some of you might know who he was, suggested Dad enroll at Cal and study chemistry and physics. Dad earned a bachelor's degree from Cal and was immediately drafted into the Navy at the height of World War II. Dad taught radio with a noticeable German accent right here at Yerba Buena, Treasure Island. One day during a class break, Dad informed his class and commanding officer that he had just received notice of eligibility for U.S. citizenship. But the letter stipulated that he must bring 2 witnesses who have known him for at least 2 years to stand up for him during the swearing-in ceremony. Dad told his commanding officer that he had not been in the country long enough to forge such relationships. His CO, commanding officer, did not miss a beat. Ensign Smith, how long have you known Strauch? 2 years, sir. Ensign James, how long have you known Strauch? 2 years, sir. Okay, the 3 of you get 3 days shore leave. Bring this guy back as a new U.S. citizen. It worked. Dad earned a PhD from Berkeley from Professor Helmholtz, but at the last minute, it was discovered that he had not fulfilled the foreign language requirement. So it was arranged for Dad to meet the chair of the German department for an exam. Dad flunked the written portion. So the professor interviewed Dad and learned that Dad's grandfather was one of the most prolific and famous writers in all of Germany. the professor said, "I cannot flunk the grandson of Alfred Bach on this day," and he signed the pass certificate. Dad joined the Society of Fellows at Harvard, earned tenure as a physics professor at Harvard, became director of a predecessor particle accelerator lab to SLAC in Palo Alto and CERN in Geneva, and was chosen to be chair of the Department of Physics at Harvard and to chair the committee that merged Radcliffe and Harvard and secured equal access admission to Harvard for women. He also chaired the committee to build the Harvard Science Center and was the United States' senior science representative to the Soviet science community during the height of the Cold War. All the while, Dad was an extraordinarily present father, along with our loving mom, Maria, who worked as a commercial artist in Boston. Tip O'Neill, the Speaker of the United States House of Representatives, asked Dad to speak in front of a distinguished congressional committee to advance the case for pure research funding to American universities, and he personally introduced Dad to that committee. After Dad's presentation, he anxiously asked Tip, "How did I do?" 6' 3" Tip, 50 pounds heavier than 6' 2" Dad, put his arm around Dad and said, "To be honest, Professor, I am not so sure you charmed them with your quarks." Dad would have a big smile and would express great amazement that this, Susan Narduli's remarkable object of art, is installed at his alma mater in his honor. Karl Strauch loved his country, his family, his work, and inspired his sons to do the same. Thank you.
Good evening. I am Hans, and on this campus, most of you, or many of you, I should say, know Roger Strauch, and I am known as Roger's brother. And I'm from the East Coast. What a remarkable building this is. Arriving here yesterday, the space was filled with students, almost every corner filled with students, buzzing with intellectual activity. You must be so proud of this building. But apparently there's a problem, because at 11 o'clock at night when it closes, nobody wants to leave. So there must be a little thing going on the campus about, students wondering, where can we hide in the Grimes Center and find a way to stay here all night? Roger and I appreciate the amount of effort and energy and talent that goes into creating such a beautiful space. It's a very complicated and challenging project involving sophisticated engineering, which we just heard about, architecture, and project management. An impressive collaboration. Today we're celebrating an impactful art installation, the result of another successful collaboration. We thought you would be interested in hearing about the process that led us to this moment. When Roger and I embarked on this adventure, honoring our father, we wanted something that would be kinetic and timeless. But we needed help identifying and selecting the appropriate artist. We hadn't done this kind of thing before. It was an experiment. In Boston, we were introduced to a distinguished art consultant who we thought would be a great partner for the project, Susie Lavacek of Alchemy Station, who is here with us today. Susie's understanding and experience elevating spaces with inspiring and engaging artwork made her a perfect fit for our project and our team. We crafted a mission statement for the artifact. Create a work of art that is inspiring and impactful, It should catch the eye, engage the mind, and lift the spirit of those who enter and use the building, even at their 100th visit. It should ignite innovation and innovative thoughts and a sense of new energy in the midst of a building that is a center of extraordinary collaboration to create a new knowledge that helps global society be a better and safer place. We reviewed 70 artists' work from 13 countries on 4 continents, narrowed the field to 13, then 4, and finally 2, who were asked to submit formal design proposals. This is the first time Susan Narduli is hearing about this. The proposals were impressive and everything we had hoped for. To us, one stood out clearly. We presented the proposals to the university without expressing our opinion. We felt it was important that the university participate in the decision-making process. And we were elated when Dean Su Jae King Liu informed us of a decision consistent with our opinion. The Hypercube by Narduli Studio. Now that the artifact is installed, we couldn't be happier. Susan, you have created a timeless, inspirational, and magical piece. It truly honors the memory of our father, Karl Strauch, who all of you know a little bit more about now, and will surely be an inspiration for Cal students for years to come. I now have the pleasure of introducing the artist, Susie Narduli.
There you go. Thank you, Hans. Thank you, Roger and Hans, for your vision. And I also want to thank the university, the College of Engineering, all the people that have helped make this possible, the architects, the construction team. We came in late with this, and we got it done. And it took a whole legion of people to really make this happen. I'm very grateful. The support has been immense. So I want to talk a little bit about how this came about and where I started when I thought about this project. My work is site-specific, so I don't really come to a project with anything preconceived. So when I first heard about the project and I read the RFP that Alchemy Station presented, I've got to say that I was a little I don't know if the right word is overwhelmed, but I was a little nervous, maybe. That's a better word. I mean, here's this project in this beautiful new building, and it's an engineering building in a department at a college, in a university that is known for innovation and creativity. This is a new building where so many of the students and the faculty would come together. There'd be collaboration, creativity, discussion, invention. And how do you create an artwork for that? So that's where it started for me, is really asking that question. How could I create something that would in any way make this hub of creativity and collaboration visual and possibly experiential? The idea for the cube itself, this suspended cube, came very early in the process. I'm also trained as an architect. I responded very much to the simple geometric forms of the atrium. I walked in there, I understood the scale of this void, this light-filled void, and it occurred to me that wouldn't it be just magical to have a suspended, very simple platonic form within that space? And I started thinking about ways that I could suspend a cube. And as the project developed, that cube became 2 cubes, and it became a Cartesian grid of pixels of light and content, and it became many other things, but that initial idea came in very, very early. You can see in this, this is actually a plan view of the piece during installation, the 2 different cubes here. And as I started thinking about this cube and how could this cube become that original concept that I had, something that would be emblematic of what is happening here at the university, I came across the concept of a hypercube, which was very intriguing to me. I had thought about this before. We create these little animations in the studio, which we call hyperobjects. I don't know that we fully understand what they mean, but the concept that this cube, this very simple platonic form, could be something that was almost unknowable, always changing. And the hypercube has this infinite number of dimensions. And to me, that was an expression of the infinite number of possibilities of what could happen within that space. And it really became a metaphor for what it was I was trying to do. This is my iPhone. So it's jiggling a little bit. This was during the installation phase. But you can start to see the content within the outer form of the cube and the inner form. There's also these little reflective cubes. They're very pixel-like. They're within the 2 cubes, and they also come out into the space a little bit in more of a random fashion. I love the idea of the relationship of something that was very organized and fixed and something that came out of that. It freed itself from that. And became a little bit more random. Here's another shot of the cubes. So I'm not an engineer, I'm not a mathematician, I'm not a scientist. And there are times when I'm asked to come up with a concept for a project that's very much out of my field. And so what that means to me is how can I come back to the roots, to the original concept, which was this engineering building? How do I create something that is site-specific? It comes out of that in a field that I really know nothing about. So I guess I'm going to just skip ahead to something I wanted to talk about a little bit later, but I think you'll see it in some future slides. It's something I call creative imagining, where I guess what it is to me is it's really about asking questions, and maybe it's the same thing that happens here, that happens with the engineering students, and it happens in other departments as well, with mathematicians and people going into space. It's like you just keep asking those questions, and those questions become like, what if? What if this was connected to this? And, what if these engineering principles had to become a light animation? What would that even look like? So in our practice, one of the things that we do a lot is we work with we do generative work, and generative work is artwork that relies on these, it's almost mathematical rules and algorithms, and the beauty of doing that is that you have something that evolves over time, but it's always new, it's never fresh, it never repeats. And that's what we decided to do for this project. So we have this grid of lights, this formal grid of lights creating these cubes, but the content itself is always changing. It will never be the same. So the software that we're using to create this piece is Touch Designer. I don't know if any of you are familiar with it or not. It's a node-based platform. And you can see if there's a set of rules, and those rules then become translated into, and this is actually a little scene from Touch Designer on the right, to information that can run a scene on this cube, and this can run infinitely. It can go on forever, and it's always going to be changing. And here's another scene from the Touch Designer editor. And what you'll see here is that we're going through a process, and we're changing some of the parameters. So we're developing those algorithms, we're developing those rules that will then inform the artwork over time. So back to this idea of creative imagining, because how do you connect the dots between an engineering school and a grid of lights? So we start with that idea of creative imagining. And these were some of our very early studies, because you have to start somewhere. We're artists and programmers. We're not engineers. So we do our research and we try to learn as much as we can and however much time we have. It's not like going to school here, but you know, we start to understand some of the basic principles of engineering, and then we start to ask those questions. Well, what if? What would that look like if we applied fluid dynamics to the algorithms, and what would that appear like? So here you have some of the things that we were exploring, and many of them have wound up in the piece. So, and in our screen, our spreadsheet, we've also got all the departments that this would relate to. We fully wanted to embrace all of the departments within the College of Engineering. And so we spent a lot of time doing that. But these are some of the, what we were looking at in terms of how we were going to develop our algorithms. And here are a few of them, and you can actually see the animations that came out of that. And you can see these in the piece. These are the animations that are actually part of the project. Now, what you're seeing is just a little capture of the animation. But as this piece over time, if we were to let this roll for 20 hours, it would always be new. So it would always be based on these same principles, but the forms itself would always be new. Like creativity, like all the creativity that's going to happen in this building. Here's the fluid dynamics. Now this was something I'd never heard about. This is apparently like a slime mold, right? Slime mold growth. But look how beautiful it is, right? And I don't know if any of you have heard of the Game of Life, but we played with that as well, Conway's Game of Life. So there are a couple of people here that I work with. There's somebody here from my studio, Kashil Shah, and Ben Price from 510, who is design engineer for the project and also built it and installed it. If you have any questions or want to say hi to them, but what I'm showing you now these are the different iterations of the Hypercube. And you can see how many variations, the potential variations, the imagination, the creativity, the building. And I truly, truly hope that this will inspire some of the students that it will read as an extension of what happens here within this building. And I thank you all very much.
Okay, are you ready? All right, so we've gotten to the actual event of the illumination now. So we're going to invite everyone to move out to the atrium for the official illumination, but wait, there's some instructions. You know, we're all professors here, so, all right. So a couple quick notes. You're welcome and encouraged to go up to the second and third floors to view the illumination, which is programmed to run for approximately 5 minutes. To maximize the show's impact, however, we're going to dim the building's lights. So for safety, we don't want you navigating the stairs when it's dark. So we're going to ask that the guests not walk or stand on the staircases once the program begins. So you're welcome to go up to any floor you want. You can walk around the floors while you're there, but please don't try to navigate these stairs when it's dark and the illumination event is going on. And then at the conclusion of the illumination, everyone is invited to join us for coffee and dessert in the lounge. The Hypercube will continue its program for the remainder of the event, and all the lights will be back on after the initial 5 minutes. So you're free to move around the building. At that time, you can use the stairs. Okay. So with that, let's thank all the speakers again, and go out and enjoy the illumination.